Welcome year 10 to lesson all about refraction. And last week we did all the stuff on stationary waves and waves, and we gave you assessment. They were the end of chapter questions, and I hope you find our worked examples helpful. And I'm afraid now we're moving on to good old refraction. Now you'll find this all in your textbook on chapter 13. Under the chapter, what's called optics, I've included a chapter front sheet in the Edmodo post. So some of this you've met at GCSE and some bits you've not met, but I'm going to presume that you've met nothing. Maybe close to the truth in some cases. Okay, so what the heck do I mean by light rays? Well, light rays, if you imagine you got a bulb just here, right in the center. I'll just get my pen here, right in the center here. You know, then light basically comes off in rays going all the way around, out like a light bulb. And you've got this in your textbook. But the way to model, and we did this for, well, they did this a lot around Victorian times, model waves, is actually look them as like water waves. And I've got a little simulation here showing what the heck I'm on about. Now, this is a ripple tank. Obviously, as in a lab, I'll be showing you a ripple tank in a lesson. I can't do, so I've got a computer simulation. Now, what you got in here, obviously you've got water. Then you've got a bar just above the water. Now, a motor goes round and round and round, and it makes this bar oscillate up and down, in the case looking on top here. As it goes up and down, it creates waves. And you can memorize yourself here. You can see these water waves moving out like this. Okay, the water waves moving out, and when they do, they hit this bar, they're going to reflect. Now, we know if you've got normal, I'll try and do this, if you're doing it with a light rays, for example, as light rays come here, the bar's just there. You can see it. There you go. It's just there. The light rays are going to reflect. Now, what you've done at GCSE, you know, the angle of incident equals the angle of reflection. Well, to model this, what we do is we use the ripple tank, and that gives us a wave model. And we can explain light by looking at waves. That's the whole point of mentioning this. So this ripple tank here is showing water waves, and you can see the waves traveling out, going along here. We can see dark and bright, dark and bright. So light can be modeled as water waves. So getting back to where I was, is when light spreads out the source here, yes, the light's coming out, and we say the direction of the wave is along here, but also we can say it is going out like waves. Now, these are not straight waves, these are now circular wave fronts. Okay? And when you do, the direction of the wave is always going to be perpendicular. Try and draw a straight line to the wave fronts as it goes out. And this is the modeling we do to explain what light does in case of reflection. So in that case, then, what you did in GCSE, you did something called refraction. Okay? Now, in the case of refraction here, what you should have done is you've got a glass block. We then draw the normal line along here, and this is called the normal. And normal simply is going to be 90 degrees to a glass block, or a transparent block here, but it's going to be glass. And then what you do is you shine a light along here, and you notice it bends towards normal just here. And then when it goes from your glass back into air again, it then bends away from the normal. Now, this is very simply done at GCSE now. You used to go a lot further, and we are going to go further in A level. And what you should have done in experiments is you measure the angle of incidence and the angle of refraction. Now, you can see the angle of refraction could be less because it bends towards the normal. In the case here, that angle R is going to be the same, and then, but this is where it can be a little bit tricky. Now, technically, that angle should be the same as that angle there, but it would be angle of incidence, and there's the angle of refraction. It's going to be bigger. And it gets bigger because when it leaves, it bends away from the normal. Now, to model this and show it how it works, this simulation is cracking. It's very old. Believe it or not, I actually found this in Africa. I know, story and a half there. When I get back, I'll tell you all about it. You're very excited. So when you've got light traveling here, and here's going to be air, and here's going to be glass, it's going to bend towards the normal. And I can see here again, the angle of incidence is less than the angle of incidence is greater than the angle of refraction because it bends towards normal. Now, what we can do to explain this is we can do wave theory. Here's like the waves I showed you in the ripple tank before. And here's the waves traveling along like this. And you can see the waves change direction when they go in from the air to the glass. Now, if you look very carefully, you should see they actually slow down. And that's why refraction happens. But why has it changed direction? Well, if you look very, very carefully, can you see the waves are slowed down here before there? And because they're slowed down here first, compared to here, that makes the wavefront bend. And remember, the wavefront is always going to be perpendicular to the direction of the wave. And because it's hitting at an angle and they slow down here first, that changes the direction of the wave, hence the direction of the light. And this really, really, really makes sense. If I now change the wave so it goes along the normal, oh, trying hard to do this, bang, 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 just got here. If I go along the normal, it doesn't change direction. Well, why? Well, isn't the wave stopped or slowed down all at the same time along here? Therefore, if the wavefront is stopped the same, well, the whole way along the wavefront stopped at the same time, it's not going to change direction. And this really explains what is happening in refraction. It's all about the slowing down of waves, or in the case of light, the slowing down of light. So that's why we get refraction, and this happens here. Now, again, if we're in a lab, we would done an experiment, and what we've done is got a semicircular glass block like this, and what we've done is shine light going in here, and then what we would have done is get back to my pen, is draw a normal line here, and I've got you to measure the angle of incidence there, and then the angle, gosh, made that line a bit longer, of refraction just there. And we use a semicircular block. Notice when the light comes out here, it does not change direction, and that's why, because it travels along the normal, like I showed in your previous simulation, because along the normal line, it's not going to change direction. Now, obviously, we can't do that, but you can, because I've got a simulation that does it. So I'm going to put this link also into the Edmodo post, and it's using a wonderful PHET software. Now, when you get to PHET software, you'll see this. You click onto here. Hopefully then, if you're lucky, the whole software will start working. And you want to go into intro. Now, what you've got here is we've got air, and here we've got water. Okay, change it to glass. Okay, it doesn't really matter which one you use, but we've done it lab, we've done air, and we've done glass. The first thing you do is you've got to change it to glass. Then you switch your light on. Now, when the light comes down here, here's going to be your normal line. Yes, it bends towards the normal. Here you've got the angle of incidence, and here's going to be the angle of refraction. Now notice you actually get some reflection as well. And this is really interesting. And this is where quantum physics helps us explain this. And it took the physicists a long time to work out what the heck was going on. You always get some reflection. Some light decides to reflect and some light decides to refract. But I'll save that for another day. It won't be part of your A-level, but you should be aware that in fact you do get some reflection. But it's very interesting. Quantum physics explains it. So what I want you to do is then you grab hold of a wonderful protractor. Isn't this exciting? Yeah, I know you love this. Now what you can do is you can set your angle, whatever it's going in here. Okay, and I'm going to do it there. So my angle of incidence now is angle of 30 degrees. Then what you can do here is you can measure your angle of refraction. Again, what you can use your protractor to measure that angle of refraction going through there. Now it's a right pig. And what you have to do is, first of all, is you put your protractor just here. And here I can see, okay, I'll do what I said before. I'm going to put that at 30 degrees. Okay. Then you got to move it and be careful of this. So you get the right position just here. Oh. And here you can measure the angle of refraction. Now 9 is about 10, 18, 19 degrees. So that's going to be angle of incidence, and that's going to be your angle of refraction. Now, going back to where I was, hence what you can do is you can do this practical. Because what you can do then is I'd like to measure sine I by doing sine of your angle of incidence, then sine R, and then I'd like you to work out sine I divided by sine R and bung them into here. Then I want 1, 2, 3, 4, 5, about 6 results. 5 would do, but do about 6 different angles. Okay, but be wary doing it. Go across like here is can go through and change the angle. You can do different angles like this. Okay. When you've done that, what I want you to do next is going back, I want you to do it the other way around. This time, I want you going from glass into air. Now, what you do in a semicircular glass block, again, what you do is you do it first of all going along the normal, so it goes in straight. But when it comes in here, here's going to be your normal line. That's going to be your angle of incidence, and that's going to be your angle of refraction, which is going to be bigger because it bends away from the normal. Now, to do that in the simulation, and you'll be incredibly excited by this, if you're not, don't care, is then you need to flip it around and try and do it. So what you do now is you take this one, is I'm going to make it water, there, and this one I'm going to make it air. Isn't that exciting? I know. So now, again, good little reflection happening, so we're going from water to air. To get your protractor, put it in the right spot, and then you can measure your angle of incidence, which is going to be 30 degrees, and then you can measure angle of refraction. Mine's about 35, 37-ish. And again, what I want you to do is go back to your wonderful results table. Oh dear, sorry. Let's work out then your sine I divided by sine R. And again, I want you to work out then sine I divided by sine R. And I want you to do the same here, is I want you to work out sine I divided by sine R. Now, I'm going to stop the video here because then I want you to look at this number you work out here and then go back and I want you to work out the number you worked out there. And I'd like you to get your thinking caps on. Is there a link between them? And then I can explain to you Snell's law. Bye.